Okay, in this video, we're going to look at a complete solution to the challenge problem number 6, where you're deriving the general equation for an ellipse based on some parameters. And that's going to actually lead into the whole goal for next lesson. Number 6 is very algebraically intensive. There's a lot, and I expect that most of you probably got overwhelmed at some point. So the goal of next class is going to be to look at this solution to number 6 and try and identify what's the overall logic, like how do you know what to do when? Like, why does it make sense? What choices you'd make? And then what are some tricks that you can use to prevent yourself from getting overwhelmed by the algebra? And those tricks are going to be helpful later on in calculus. So you feel probably overwhelmed by number 6 right now. Hopefully by the end of next class, you'll at least be able to look at number 6 and say, I think I have the moves that I need to be able to do something like that on my own. So problem number 6 is a generalization of this sort of thing. I said we've got a focus at 0, 8, and a directrix at y equals 2, and then we've got our distance 1 and our distance 2 to some arbitrary point on our curve. And I said that distance 2 has to be 4 times as big as distance 1. Okay, so you'd know how to set this up with numbers. It would be something like this. We've got this kind of Pythagorean theorem-based distance, and then d2 is just a vertical distance, so it's the height y minus the height 2 gives you that red distance 2. Except problem 6 didn't actually use numbers. It replaced all the numbers with parameters. So instead of a height of 8, we have a height of c, and instead of y equals 2, we have y equals n. But the setup is going to be the same. Okay, so to make this video short enough, I'm not going to be writing out all the algebra. I'm going to be pausing the video. And your goal is not to try and reproduce this yourself as you're watching the video. Instead, I want to highlight for you what the overall strategy is and what some of the techniques I'm using are. Okay, so this already is an equation for whatever shape this makes. And the problem told you it was an ellipse. So this is actually the equation for an ellipse. But the problem is it doesn't look like an ellipse. I wouldn't look at that and say, oh, that's an ellipse. So what are we doing when we're doing algebra here? We're not trying to solve for anything in particular. Instead, we're just trying to take this equation and make it look different in the hopes that we can turn it into an equation that looks more familiar, like it connects with something that we already know. So like one thing you might try, so if we didn't know it was an ellipse, one thing you might try and do is eventually make it look like this. Something times x minus something squared plus something, because you know that that's a form for a parabola, and each of these numbers here has a particular meaning for the parabola. So if this was actually an equation for a parabola and you could make it look like that, you would have learned some things about your parabola. You know that this is the equation for a circle that's centered at the origin, and an ellipse is really just a stretched circle. It's a transformed circle. So what we're hoping is to take this equation and make it eventually look something more like that. Except, of course, that's a circle, so what ours would really look like is we'd have some scale factor times x, and we'd have some scale factor times y, and those would end up being different, because if we were scaling x and y by the same amount, that would just be a circle scaled to be a different size. So we're looking for 2 scale factors on x and y. And remember, it doesn't have to be centered at the origin. So if we were going to take this equation for a scaled circle and shift it somewhere, it would actually look like this. We'd have some scale factor times x minus a shift amount squared, and we'd have a scale factor times y minus a shift amount squared equals some constant on the other side. So in my notation, all of these blobs represent constants. If you look at a textbook, the textbook will show it in this form, but really that's the same thing. Like imagine that my coefficient here was 2. That's exactly the same as dividing by 1/2. Or imagine that my coefficient here was 1/4. That's exactly the same thing as dividing by 4. So having a scale factor in the front that's being multiplied versus having a scale factor that you're dividing the entire term by, those are actually equivalent to each other. The textbooks often like this format. I don't think it really matters either way. You should be able to recognize both. Okay, so the point though is we're trying to take this equation and we want to eventually make it look something like this, because if we can, this will tell us stuff about the ellipse that we know that this already is. In particular, it will tell us, like, how have we shifted the ellipse, and what are the scale factors that are creating the ellipse from a circle, and so on. So that sets your goal for the algebra. We're not trying to make it look like y equals something because we know it's an ellipse already. So instead, we want to try and simplify it until all the x squareds are sort of together and all the y squareds are sort of together, and then we've got a constant. Okay, so I think my first move here is I'm going to square both sides. And I think I'm going to distribute the 16 in here because I'm hoping that I can expand all of these terms that are squared, because eventually I'm hoping to be able to combine things together. So in order to expand everything, I have to distribute all the things. So let's do that. I might as well expand both of those, and then I'll try and start subtracting things and combining them. So let's expand both of those now. And I'll go ahead and distribute that 16. Okay, so it might felt like we've made this equation a lot worse because this looks really big and complicated compared to where we came from. But remember the goal. The goal is I want to group things together so that way I can start combining them by factoring or by completing the square. So expanding everything out was kind of a necessary step in this strategy. So let's go ahead and move all the terms with x's and y's in them over on this side, and all the terms that don't have x's and y's over to the other side. So it looks to me like these are the two terms that are constants, because remember, c is a number, it's this y-coordinate, and n is a number, it's that y-coordinate. So 16c squared is really just a number. So let's move all the numbers over to this side and move all these things over to that side. So I think I'm going to subtract a y squared from both sides. So this 16y squared minus y squared is going to give me 15y squared. I'm going to start crossing things out as I deal with them. So I got the 16x squared, I've got that. Let's add 2yn over to this side. So now I've got 2yn minus 32yc. So took care of that term, took care of this term. And now let's subtract 16c squared from both sides. So n squared minus 16c squared. All right, so how are we going to deal with, so this is just a number on the right-hand side because n is a number and c is a number, so all of that just ends up being a number. So how are we going to deal with this? I've just got a clean x squared. There aren't any other terms with x. I've got a clean y squared. But how are we going to deal with these two terms that have y in them? Remember, eventually we're hoping to have this look like a scale factor times x squared plus a scale factor times y squared. But remember, the y might be shifted, so it might be like this. So how do we get something that looks like that? Well, I'm thinking if I've got a y squared and I've got some terms with y in them, probably I need to complete the square. So let's start by factoring out the y from here. Okay, so there we go. So I took this and I rewrote it that way. How do you think about this? Remember, n is a y-coordinate and c is a y-coordinate. They're both just numbers. So let's imagine that n equals 30 and c equals 1. Then I'd have 60 minus 32 is 28. So really, you can think about this 2n minus 32c as being a number, like saying 28y. And so if we're going to complete the square, if you have 15y squared plus 28y, this seems a lot easier to complete the square on than if you have 15y squared plus bleh, like this thing times y. So this is where the blob strategy comes in. Let's define a new term. Instead of blob, let's give it a letter name. So I'm going to define k equals 2n minus 32c, okay? So now I can rewrite my original equation here. Okay, so the 16x squared is still there. This stuff is still there. 15y squared is still there. But instead of this thing times y, I'm now writing it as k times y because I defined k as that thing. Okay, let's complete the square. If there wasn't a 15 here, that seems a lot easier. If I'm just completing y squared plus ky, that square is very easily, or we can complete that square very easily. It's going to be y plus k halves squared minus k squared over 4. The problem is that 15 there is kind of messing us up. So let's do this. Let's factor out the 15 temporarily. So I could rewrite this as 15 times y squared plus k over 15y. And then I could just factor out that business in there. I kind of don't like, it looked so nice when I just had a k and then I messed it up when I factored out the 15. Let's go backwards and factor out the 15 earlier so that we can define our k so that it still looks nice. Okay, so here I factored 15 out of both these terms. So the 15y squared now becomes y squared. And then 2n minus 32c becomes 2n minus 32c divided by 15. Okay, so now I can define that thing as my k value. See? And now that's a lot nicer. Let's complete the square. Okay, now I've completed the square. And we just factored out the 15 to make it easier to complete the square, but I'm still in the process of trying to group all the things and have all the constants on the other side. And so here I notice I've got a constant. K is just a number, because it is based on just numbers. So k squared divided by 4 is a number. So that feels like something I need to move to the other side because it doesn't involve x or y. So let's redistribute the 15 so that way we can resume what we were trying to do. So this term over here, I stopped writing them because I didn't want to have to write them down every time, but this was still 16x squared. Here I'm going to distribute this in. So this is 15 times y minus k over 2 squared. I multiply the 15 here, so this is 15k squared over 4. And this over here was n squared minus 16c squared. All right, so now I can add this term to both sides. So it disappears from this side, and on this side I've got 15k squared over 4. There we are. And let's go ahead and scoot these over so that the whole equation looks nice. Okay, so I still haven't substituted back in for k, because remember, k is all of this other stuff. But the equation is looking a lot nicer, particularly if you think about all this stuff on the right-hand side as just being a number. So if I cover this up, now it looks like a familiar form. I've got a scale factor times x squared plus a scale factor times a shifted y squared. And that looks a lot more like we are expecting an ellipse to look. Let's see if we can't simplify this stuff over here a little bit. So I'm going to plug k back in and see what we can do. All right, so I'm noticing that these have a factor of 2 in common. So let's factor that out. And now that I've done that, I see that the 2 that I factored out is still being squared. So it's actually 2 squared. So that divides the 4. So that's nice. So maybe I'm just going to rewrite this part here. Okay, so this seems kind of interesting here and here. This seems like it can be, like we should be able to do something with that. So one choice is we could expand this and try and see how things cancel. Instead, I'm noticing this is a difference in squares. So let's try and write this as n minus 4c times n plus 4c. Let's just make sure that makes sense. So that's going to give me n squared plus 4nc minus 4nc cancel each other, and then minus 16c squared. So that works. And so then I've got 15 times n minus 16c times another n minus 16c, because that's, whoops, because that's what it means to square something. So now I'm noticing that we've got, it doesn't quite work, does it? Oh, you know what I'm realizing? I'm realizing I've made a mistake here. When I substituted back in for k, I forgot that k was being divided by 15. And here we have k being this expression has a 15 in the denominator, and k is being multiplied by 15. So actually, I think that 15 is going to cancel, but then we still are going to have another 15 in the denominator because the k was being squared. So really, that's going to end up being 1/15 times that. Okay, well, I've lost all my excitement about trying to simplify this because I thought things were going to cancel in a cool way, but it doesn't look like they're going to. So I'm back to, like, let's just leave it at this for the moment. I am actually going to let p equal that thing on the right-hand side. So now I can really write my equation in a new simplified way. I can say 16x squared plus 15y plus k over 2 squared equals p. Doesn't that look a lot nicer? And if you want to make it look like the textbook always has a 1 on this side, so we divide through by whatever constant is on the right. So if I divide both sides by p, now I've got 1, and this is over p, and this is over p. And again, p is just a number. What number? Oh, it's this gross number, but really at the end of the day, that's just a number, so it's totally fine to just write it as p. Okay, so that's the process. In class, we're going to focus more on kind of what was the strategy here, and what were some of the algebraic moves that made this possible and possible not to get overwhelmed by. But I want to remind you what the big picture was. The big picture was we had some geometric conditions, and we wrote an equation. And this equation is already the equation for whatever the graph ends up looking like. And since we know it's an ellipse, we know this equation is already the equation for an ellipse. But looking at it doesn't tell us anything about the ellipse itself. And so we went through all of this simplification to get it to look like this. And this equation is equivalent to what we started with, because that's what you're doing when you're doing algebra. You're just changing what each side looks like without actually changing the values involved. So now that it looks like this, we've learned something about our ellipse. We've learned what the two scale factors on x and y are, so kind of how close is this to looking like a circle. And because 16 over p is very similar to 15 over p, like those are almost the same number, I would expect this to look very close to a circle. It's not going to be like very elongated. The other thing we've learned is that the ellipse is centered horizontally. So it's centered on the y-axis because the x amount hasn't shifted left or right at all. But it looks like we've shifted up by a value of k over 2. And what is k over 2? So k is this. If I divide k by 2, that's going to divide the 2's in the numerator here. So that would just be n minus 16c over 15. So this number, which is made up from an n and a c, which remember were our original coordinates. So now that I know what the c and so I could tell you what the c and the n were, and you should be able to tell me what the vertical shift is for that ellipse because of all this simplification we did. All right. Good luck.